Hello everyone, and welcome to this new video where we are going to discuss some subjects in physics. So a few days ago I came across YouTube video that was describing a magnetic phenomenon. It's not the first time that I discuss magnetism, but often magnetism is actually, uh, for good reason, a subject of debate. And electricity and magnetism in general are very difficult topics to uh, to understand and to integrate. And that's what I would like to discuss. So the topic of today has to do with an explanation that is found in secondary school at secondary school level in the UK. So this comes if you in terms of keywords. This comes when you type something like the motor effect GCSE. So GCSE would represent the kind of end of secondary school level at around age kind of 16 or so, maybe 15, 16. And so we are going basically to look, at a few videos together that are very short clips, just to show you essentially that it's not like I picked a specific video that was giving this specific explanation, and then somehow I picked like kind of the wrong one, and then all the rest are fine. It seems to me that there's something a bit strange in the explanation provided, and that's what I would like to discuss very quickly. So let's have a look at the first video here. I'm going to put the sound quite high just to be sure, and let's listen to it.
Find out the direction of the force and its strength. Now, we saw in the last video on electromagnetism that a current-carrying wire will produce its own magnetic field. This means that if we place the wire between the north and south poles of two magnets, which will also have their own magnetic field, then the two magnetic fields will interact. This interaction results in a force on the wire, which will effectively push it out of the field. However, to experience this pull force, the wire has to be at exactly 90 degrees to the magnetic field.
Okay, so let's stop here. So that's one particular account.
I'm showing you here a wire carrying an electric current. The arrow shows the direction of the conventional current. Remember that there's a magnetic field around this wire, but we're not showing it. We've now placed the wire into a magnetic field. The magnetic field around the wire now interacts with the magnetic field between the magnets. This means that the wire now experiences a force. In this case, the force is in the upward direction. This force would cause the wire to move upwards. Scientists call this the motor effect, and you could be asked that in your exam.
Okay, so that's another one. So let me check something. Yes, okay. And then let's have a look at another one here.
Current flowing through the wire. We know that this will create a magnetic field in the wire because of electromagnetism. Now we have the magnetic field of the magnets and the magnetic field of the wire interacting. There's going to be an interaction between these two fields, and that will create a force on the wire.
Okay, so that's another one. Then another one here.
Will form concentric circles around the wire. Okay, now if I was to take this wire that's generating a magnetic field and place it into a different magnetic field, then the two magnetic fields will interact with each other. So the magnetic field of the wire will interact with the magnetic field of the two
Okay, so basically that's the same idea.
Effect is when a wire with current flowing through it is placed in a magnetic field and experiences a force. A wire with current flowing through it is often referred to as a current-carrying conductor. It normally means a copper wire. The magnetic field is produced around the current carrying conductor. When placed inside a magnetic field, the magnetic fields interact, and the wire experiences a force, causing it to move.
Okay, so in any case, that's kind of the bottom line of it. So what is it that I want to discuss here? Well, like in all of these descriptions, what they actually said is you take a wire. So let's say this is a wire, and then I don't have a magnet here, but basically you put it inside a sort of magnetic field that is perpendicular to the wire. And the notion is that the magnetic field that is generated by the wire is going to interact, that's the word being used, with the pre-existing magnetic field from a magnet, for example, or from two magnets. And I think here there is quite a bit of a problem at the very least, in the terminology being used. So first of all, that's the only explanation that is given. Okay, so allegedly there is an explanation. We are told that the magnetic fields are going to interact with each other. So that's kind of step one here. And then the step two is that somehow these interactions between the magnetic field is actually going to generate a force on the wire. That's what we're told. This is generating a force on the wire. And basically that's it. And we don't know exactly, how is this coming about and so on. So I think this is quite problematic, to be honest. And there are two issues with it. The first one is that even if we assume that the magnetic fields are going somehow to interact with each other, then basically it does not explain how interacting magnetic fields are going to cause a force on the wire. Because we are told so far that the wire generates a magnetic field. We are not told how a magnetic field is going to affect the wire. And even if the magnetic field were to be deformed or these magnetic fields were to interact, essentially we reach a sort of dead end because we don't know how these magnetic fields interacting with each other are going to affect the wire itself. Okay, so it seemed to be a bit question begging, as people would put it in philosophy. There is another aspect which is basically taking issue with the notion of basically that the magnetic fields are going to interact. Interaction here, I mean, it's not a word to be thrown like this, like it means anything you want. Traditionally, at least in physics, or even to be honest in real life, if you interact with something, it means that you're going to affect that thing. Okay, you're going to change the state of that thing. If you interact with a pen, the pen maybe used to be on the table, and then I'm going to interact with its state of motion and position to be put at different locations here. So what that means here is that if I consider a magnetic field that is generated by the wire and a magnetic field that is generated by a magnet, saying that these two things interact with each other is basically saying that the magnetic field from the wire is literally changing the magnetic field from the magnet. And as far as I'm aware, and it could be that my knowledge of electromagnetism is not as good as I thought it was, but as far as I'm concerned, within traditional, classical, and in fact even quantum electrodynamics, at least in vacuum, I'm not aware of any phenomenon where a magnetic field is going to change the magnetic field of another kind of object. Okay, so a magnetic field generated by one object is going somehow to change and alter the magnetic field generated by another object. So I'm not aware of any phenomenon like this in classical and even quantum electromagnetism, especially here in this kind of setup where everything is supposed to be basically in vacuum. Okay, so what do I think people mean here? I think that, so again, I like to take as much as possible a so-called charitable view about these things. And so what I think people are actually saying here is that there are two ways to calculate. I mean, there are two ways you can conceive of calculating why, or stating why a particular force is acting on something. And the first one, which is the one I've adopted, I'm going to show maybe a video here of something I've shared a few weeks or months ago that was exactly on that problem. How is it that a magnetic field makes a wire move? And that was given that we are told in principle that magnetic forces do not do work. Okay, so that's something that I've explored quite a bit a few weeks ago. So this view essentially postulates that a magnetic field is going to exert a certain force on basically freely moving charges like electrons or whatever you believe the current is made of in a conductor. And basically that's it. So if you have freely moving charges, then they are going to give rise to this to a force in a magnetic field. Okay, they are going to be subject to a force in a magnetic field. This is called the Lorentz force, and this Lorentz force can be, and that was the subject of my video, can be actually explored further on how it gives rise to this force, this motor force, basically onto a wire. Okay, now the other one is a bit different. It's a different picture where we postulate the actual energy, magnetic energy everywhere, if you will, in the universe. Okay, so we postulate a form for it, and as it turns out, this postulation is like basically the integral of b squared over 2 mu 0 over the entirety of space. And it doesn't work always, this particular expression. And here, because it needs to vanish, for example, at infinities, etc., there are plenty of things that in principle you need to be careful about. Otherwise, you need somehow to take these infinities and put them kind of under the rug or something. But when you apply this, then essentially you can actually explain that when you've got a wire like this that is traversed by a current, is generating a magnetic field, then there is another uniform magnetic field that is applied onto it. What's going to happen is not an interaction between magnetic fields, it's actually a superposition. So these magnetic fields are going to add up. So you simply add up these magnetic fields, and then you evaluate the magnitude of this addition of these magnetic fields, the magnetic squared, in fact. And what you do then is you integrate everywhere. So you add up this magnitude of the magnetic field squared, you basically sum it up over the entirety of space. And then what you do is that you consider the wire and the magnets as being so-called boundary conditions for the magnetic field B. And then you change these boundary conditions. And you try to see which changes in the boundary conditions are going to lower this particular magnetic energy, or total magnetic energy, if you will, of the universe, or this kind of mock universe with one magnet and one wire. And so in that case, you can kind of explain how things kind of go along. But usually there is not a sort of dynamical view of what's going on. It's rather a static view where basically we model things like a wire, things like a magnet, essentially as some sort of boundary condition in a sort of mathematical model. And again, one of the issues with this is that, for example, if you imagine a uniform magnetic field that is basically that covers the entirety of space, right? And then you actually put a wire with a current there. In principle, the force version of the explanation is going to tell you that the wire is going to move, let's say, up or down, depending on the direction of the current. Okay, and that's again something I've explored in the video I've showed earlier. However, if you use the variation of magnetic energy thing, then you're not going to observe anything, because if you have a uniform field, magnetic field everywhere in space, and you actually imagine changing the position of a wire, then you've got what is called translation invariance. And this translation invariance is going to tell you that nothing is going to change in the physics of the problem as you move the wire up and down, for example. So there are situations that are obviously idealized situations, but that basically can't be worked out with this notion, or at least what I believe these people are trying to say, that you look at the magnetic energy in the entirety of space, and then you look at what variations in, for example, the configurations of the wire and the magnet are going to lead to a decrease in magnetic energy. So I think that's what they actually did. So basically that's it. So I think this is problematic. As far as I could see, this is essentially like a very commonly spread explanation about this, about the motor effect. And I think that if anything, this is not, I think, a good or accurate explanation. I'm not saying that people need to go into huge details, but I think that there are simpler ways and that are accurate to explain what's going on. But clearly, interacting magnetic fields, in my view, is not a proper way of explaining what's going on. And I'm a bit saddened that this is actually in national exams for GCSEs in the UK. Now, it could be that I'm missing something. I've just used here my own knowledge of electromagnetism and electrodynamics. If any of you has any idea what this is actually trying to say, and that's not what I proposed, then by all means, do let me know in the comment section. I would be really keen to read what you've got to say. Otherwise, see you in the next video.